All good? Welcome to the final track for Sunday before lunch. This one's actually a really interesting one for me because I've been to a few functional programming talks and I'm still utterly mystified. So I'm really hoping that Eugene can take care of that. So please make Eugene feel welcome.
Thank you. All right. So it's my first PyCon, so I'm a bit, and my first time talking, so I'm a bit woohoo. A few months ago, I attended another conference called LambdaJam, which advertised himself aims at expanding the skills of functional programmers. I'm not a functional programmer. I would call myself FP curious, but I decided to attend essentially because there's a welcome to FP day, and I said, yes, that's for me. And there was a guy called Yaron Minsky running an introduction to OCaml, which is the language I'm interested in because it comes from France, and Haskell is from England. So I just went, and that's the story of my time at LambdaJam in some ways. The highlight of LambdaJam for me was to meet Eugene Chang, who's a mathematician, whose core specialty is category theory. If you hear functional programmers talk about programming, they talk about category theory all the time. I'm still struggling to make the link between the two, but we'll see. And she was absolutely awesome. She gave a keynote on using category theory, so leaning on very abstract mathematics to understand the social justice issues, which was very interesting. If you have a chance, watch it. She wrote 3 books now. I've read her first 2, How to Bake Pi and Beyond Infinity. I'm looking forward to reading the next one. If you take anything from that talk, is read Eugene Chang. She's awesome. The following 2 days were horrendous. For 2 days, I just held my head in my hands, thinking, oh, what am I doing here? I must be completely stupid. I opened up to one fellow attendee who attended LambdaJam for the first time the prior year, and he told me, you need to watch Professor Frisbee. What is Professor Frisbee? Professor Frisbee introduces composable functional JavaScript. It's a course that teaches the ubiquitous abstraction for modeling pure functional programs. Functional languages have adopted these algebraic constructs across the board as a way to compose application in a principled way. Let's stop there. The truth is, it's a claymation hedgehog
I have some news for you,
speaking
class.
to
You've
toys.
been using Monads.
So halfway through 2 hours of claymation hedgehog, you're supposed to be enlightened as to what functional programmers are all about. And in some ways, you get there. When you have a 5-year-old in the house running around, it's a bit like a magnet. Wow, what is that, Papa? What is that? Yeah. I'm worried I turned my 5-year-old into an Haskell developer. Hopefully not. So we're going to, in the remaining time we have, cover as much as Professor Frisbee, but not in JavaScript, in Python. It's a very distilled version of the course, obviously, and all the credit for what I'm going to present, so all the good stuff really should be credited to Brian Lonsdorf, the guy behind Professor Frisbee. The misrepresentation and mistakes are all mine. Let's start with functors and illustrate functors. So here we have, yeah, it's big enough. We have a beautiful function called nextChar from string, which takes a string containing an integer and returns the next character when you increment the integer in the string. So that's one implementation. You strip the string, then you cast it to an integer, you add 1, and you return the CHR of the given integer. And it just works, which is awesome. Functional programmers would have issue with that. Strip, cast, inc, like they're all temporary state in some ways. We don't like them. There's very many ways that functions are called. So here we have a method call, we have a function call, we have an operator usage. It's not that great for a functional programmer. So we say, okay, that's all right. We can use straight function. So we could use, hey, int f.strip, and here we go. It's just functions. There's no state. It's fantastic. Yeah, but it's a nested mess. So what would a functional programmer do? And here we have to introduce the concept of a box. And I'm not going to say too much about the box. I'm going to illustrate what the box does. And also, we need to define one function, the identity function, which given x returns x, which is pretty straightforward. And as a warning, if you were in the talk yesterday about refactoring Python code, the code I'm going to show you is definitely not something you want to write at work if you work in a Python shop. So I'm going to write a named anonymous function identity. Up and why do I do that? Because functional programmers absolutely love their anonymous function. Bam. What's a box? So a box is something, and I'm going to use a very loaded word here. It's a type, and you can put something in a box. So if I put 1 in a box, I've got a box containing 1. What do you do with that type? Well, you can map over the type. If you're a Python developer and you know the map keyword, you think map, you think iteration, or at least that's how I was thinking about it. But really, a functional programmer thinks about map as composition. And all you want to do is, when you call map, you want to apply a function to something. So let's apply an anonymous function. Oops. Anyway, we get a box containing a 2, which is fantastic. But most of the time, we don't really want to keep things in the box, so we want to get them out of the box. And we can obviously change the call. So I'm going to change another call for kick. Up. Oops. We get a box with a 4. So, OK, so we've changed our operation. We've composed functions. So composition is awesome. And then we need to extract that thing out of the box. So what we're going to do is we could call fold with the identity function, and it return whatever was in the box. So fold is to extract the value from the type that you were using. Calling fold.identity at the end of every composition of function is a bit horrendous. So you can also obviously call fold with a function that does something, and you get what you want. So that's what a box is. So a box is a type that you can use to compose functions and then to transform a value, and then you get the expected result. So let's implement our next car from string using the box type. So what do we do first? Well, we're going to put box in the type. Up. So we've got a box containing a 64. All right. We need to strip it. Oh, much better. Look. Next, let's increment that correctly. We're going to cast it. Oh, well, I can do that. We still have a 64, but now it's an integer in there. And then we're going to increment. Oops. And so just run that, we use 65. And then we know we want to extract, so we're going to fold. It's the last operation, the last function we want to compose. And that's the CHR function. Wow. And now we feel so happy. We've got a very linear data processing pipeline. Functional programmers would rave about that. It's awesome. And I don't know, there's something to say about it. Like, it's kind of nicer than that one, which was deliberately made quite ugly. Efficiency-wise, I'm not so sure, but at least we understand something. So when we're a functional programmer, we want to lift values into types, and we want to compose functions and then extract the result out of it, which is pretty neat. Box is a functor. So what is a functor? So I implemented one very silly, but basically it's something that can be mapped over. So all you need is to have a map function, a map method on it, which obey 2 properties, the identity law and the composition law, which are presented here. So you can compose several functions, or you can, and if you call the identity on it, nothing changes. You get the same functor. Awesome. Before I can keep on going talking about functors, I need to do a little detour through the concept of currying. So let's say we have a function called add, which is very convoluted, adds 2 numbers, and we want to specialize that function. And that's something that's quite commonly done by functional programmers. So you have a very generic function that does lots of things, and you specialize it to use it in a nice place in the right way, giving it a proper name. That's kind of neat. So we define an increment function based on add, which basically adds 1 to a number. So when we can call add with these 2 arguments, and you can just use increment with this 1 argument, and you get the expected result. It's kind of neat. That's what a Python developer would do. someone who has a little bit more experience about the standard library would say, hey, you know what, it's like partial argument application, so I can from functools import partial and define inc as a partial of add, to which we, with the first argument having the value 1. And that's really, like there's something really, I think, beautiful about defining inc as a one-liner using partial. Like it makes me feel very smart. Can we do better? Wouldn't it be even better if we could say, you know what, increment is just add of 1? Oh, that would be really neat. And now that's Python code you really don't want to write. One way to do that is to use closures. So we define add as not a function of two arguments, but a function with only one argument, and which returns another function, which also takes one argument, which actually does the work. So when we do that, we can define inc as add called with 1. The only problem is that then calling add becomes really a bit ugly. Like we have to say add of 1 and then add of 3, which, yeah, not great, but you know what, why not? We want to become functional programmers. So, and because functional programmers love lambdas, I can do everything in one line, and it's really awesome. So I've got a lambda of x, which returns a lambda of y, which is the x plus y, and increment is just add 1, and it's all absolutely beautiful. Let's illustrate that with something a little bit more realistic. So let's define a replace function. We take a pattern and a replacement string, and in a string, we'll just replace all the values. So what we want to use really is resub, which has exactly the signature we want, pattern repl string. But it's not curryable like that. Like it's not a function we can curry, but we can redefine a function using it that we will be able to. We should have a curried form. So replace is, and my lambdas, I love them. Pattern, lambda, oops, repl. You really don't want, like, code review, like, poof. All right, so we've, oh, what have I done wrong? I missed a column. Whoop. There you go, thank you. So we've got a replace, and then let's specialize that replace, because it's a very generic replace. Like we want to specialize it, and we want to create a sensor. And a sensor, like let's make a really smart sensor, someone who really doesn't like vowels. Oops, no. And because it's a curried form, I need to do that. Oh, that's horrible. So we now have, and when we do that, we specialize replace. It's kind of neat. Like if only we didn't have to put these brackets everywhere. And so we can use the sensor to censor any string we want. So let's censor PyCon AU. Boom. Oh, PyCon is censored. Awesome. Uppercase is OK. It's just lowercase. There's got a serious issue with them. So really, like, there's a lot of you can turn any function into basically any function into a curried form. So let's do it for map, and we talked about map a bit earlier, and we know that map takes a function, oops, and an iterable. I'm going to do that because I know that what we get is a map object in the end, and then I can lambda things. Oh man, I love my lambdas. Bam. So we've defined a curried form of map, which is cool, and we can define a sensor all, which is a specialized form of. So use map plus our specialized replace, which is sensor, to replace a list of things. So sensor all, and we're going to say, oops, lambda list. Oops, not what I wanted to do. Sorry. And what it does, it's map of sensor, and that's cool. And then if we do sensor all, poof, oops. What have I done wrong? Oops. Oops. What have I done? Stress. Up. Here we go. You know, like live presentation, you can, I was ready. I can do it, I can do it. So why did we go through that little currying detour? Is because there's another dimension to functors. So at the moment, so far we've used functors as let's put a value in it and apply a function to it. But functors can also be applicative functors, which makes them even better. So what's an applicative functor? It's a functor which has an apply method. So here typically we have a functor f in which we lift the function f, which we can apply to a functor of a value x. And it's exactly the same thing as if we have the functor of x, so in which we lift x in the functor to which we apply the little function f. A little example, so let's define a square. No lambda here, no code smell. So if we put 2 in a box and we map square over it, we get what we want. And we can also lift the square function into the box type and apply to a box of 2, and we get exactly what we want, which is really neat. So one argument, no big deal, but it's a neat thing. So the reason why we needed currying, so box is an applicative functor, obviously. The reason why we needed currying is what happens when we have more than one argument. So here we have a lambda define, which is our, add define, which takes 2 arguments. And if it was not in a curried form, we wouldn't be able to apply it. But in its curried form, we can. So we can say, we can lift add into box, and we can apply it to a box of 1 argument, and it's valid. Like it's just, because it's carried, it's valid. What we end up with a box that contains a lambda, which we can then apply again to another box which contains something else. Poof. And we get a box of 5. So when we add 2 plus 5 plus 3, we get 5. That's awesome. So that's an applicative functor. That's all they are, really. Like, it's really neat. There's a lot of little bit of, because it's a bit convoluted to do that. A lot of functional programs contain the little helpers, such as with very explicit name, like lift A2. And what lift A2 does, takes a function and 2 functors, and we lift the function into an applicative functor and apply it to the two given arguments. So it's lift and apply with 2 arguments. So for example, here, let's write a lift A2 that will add, when called with add in box of 3 and box of 4, we'll return box of 7. We could do it by saying, hey, you know what, we know it's a box, so we can put it in the box, and then we apply box, no, not this, sorry, f of x, and apply to fy, poof, and we get box of 7. But we've made an assumption here. Like, it works for my example, but to put f in a box, we need to know that the functors that we're going to apply it to are of type box. So it's not really that great. We could do introspection, we could do some magic, but there's another way, because it's an applicative functor. What we can do is we can say, well, it's f of x, to which we map f, which we then apply to f of y. And that's magic. And it's only because you have functors and you have applicative functors, and you just, they mean the same thing. It's kind of neat. I was ready in case I could mess that one up. So we've seen functors, we've seen currying, we've seen applicative functors. Next, we need to talk about eithers. And either is left or right. What does that mean? If you have a right, if you lift a value into a right type, so let's say we lift 3 in a right object, and then we compose several functions, adding 1 and divided by 2, we get a right of 2. What happens if you do that with a left? Well, you get a left of 3. Oh, why not? Why? Right is the right way. Left is the wrong way. Like, the either captures the concept of disjunction. Like when we have programs and we follow different paths. When you don't know which path you're going to follow, well, you use an either. I'm going to illustrate. Here, I'm importing random, and random will choose either left or right and map the things. So I'm going to run it a few times. So okay, we got right and left and blah, blah, blah. But as we know, at some point, when we're a functional programmer, we need to extract the actual value, the thing we want to play with, from the type. And to do that, we fold. But here, we fold, but it could be a left or a right. Should we do the same thing? Well, we don't want to do the same thing. So fold, when you use an either, takes 2 functions as its argument. One that will be executed if you end up with a left, and another one which will be executed if you end up with the right. So let's use the best Canadian swear word. And just, well, let's just use identity here. Poof. So we get tabernacle if we get a left, and come on, and 2 if we have a right. When would we want to use that type of things? But typically when you can have a null value. So you can define little helpers that's from nullable, which takes can you see that? Which takes a value, and if that value is none, returns the left of that value. If that value is right, return the right of that value. A little illustration of that. So let's say we have a dictionary of non-colors, and we want a function that takes the uppercase of the hexadecimal part of the color. We can write that function. So naively, we could say, oh, let's just put it in a box. It's not going to work, but we can put the color in a box blue. Oops, that's not what we want. We want non-colors. Get color, up. And then we'll map. So we want lambda, so it's a string. We want to remove the first character. Boom, and then we want to operate. This composition is awesome. Lambda string, s.upper, up. And that's what we wanted. So really here, we're folding. That's cool. What happens when you have a non-value? Error. Makes no sense to subscript none. So what you will want is say, hey, we've got that from nullable here. Let's just use it. And naively you run it, and you get a type error. Why? Because fold takes 2 arguments. So we just need to add 1 argument here. We have an error, and we're going to say it's unknown. And now it just works. So illustrating the concept of either, we've got, it looks like you have one single flow one single processing pipeline, yet there's a disjunction in there, and it's kind of neat. Well, functional programmers will rave about it. Another use case where you'll want to do that, and in Python, it's in everything, but in Python especially, you're using exceptions. So we can define a try-except helper, which takes a function, which when it's called, will try to run the function, and if there's no exception, will return the right of the value returned by the function, otherwise a left of the exception. So let's define a little helper read, which will read a file, and we're going to have to import JSON, and that's unsafe Python code, but that's okay. Like, it will read a configuration file, get the port if it exists, and returns what it is. How will you do that in a functional style? Well, you'll put it in a box. I love that box. And then what do you do? Well, okay, it's JSON, so we have a string. Yes. Boom. So and then we can fold again. Up. And it's a configuration. It's c.get port. And if there's no port, let's get 3000. Bam! Fantastic. What if we have a file that doesn't exist? File not found error. It doesn't work. So we want to put it in a box. We don't want to put it in a box directly. We want to use our little helper, our try-except helper, which takes a function, which when called, will do the work. And then, because we know, we've learned now from a mistake, we have the left case, and now it works. It's fantastic. What if you have invalid JSON? We have a problem here in the JSON.load. What do? We have a try-except. Let's just use it. So we can say, lambda is here, and it's not just that. It's a try-except of a function which will do the work. Why doesn't it work? What's going on? Oh, we have a left. Why do we have a left? Well, because it doesn't work. But what's going on here? Let's have a quick look. So let's remove the fold and see what happens. Oh, we have a right because the file does exist, but then which contains a left because it's not valid JSON. What could we do? We need to chain instead of mapping. What chain does is it will apply the function to the type, but return another type, which is really neat. And in that case, we can then fold properly and get exactly what you want. So either as an extra method, which is called chain, which makes it a monad. I promise you. 5 minutes, perfect. Let me try anyway. For a type to be a monad, you basically need to be able to lift into the type. So you need to have that off thing, let's say type.off, and you lift a value into the type. And you need to be able to chain, sometimes called flat mat or bind or that squiggly wiggly thingy, I think it's Haskell. And if you have a type which allows you to do that, so you can actually, by calling chain, you can join a type to another type by calling the appropriate function, then what you end up with is a monad. That's all you need to know. It's pretty cool. Like when you think about it, it's okay. So all we need is to lift things, put something in a type, and then have a fold and a map and a chain, and we end up with things that are pretty cool. Since I have a little bit more time, which is awesome, I thought maybe I would stop there in my rehearsal, so that's cool. We can go a bit further. Semigroup. So yes, functional programmers love abstract mathematics, abstract algebra, and they deliberately use vocabulary from that domain because they think it makes it a lot easier for people to talk about programming. I'm not there yet. I might get there, but I'm not there yet. What is a semigroup? Well, again, it's quite simple. It's just something that has a concat method. So let's just add another one to the fray. We've got map, we've got fold, we've got chain, and we've got off, and we've got concat. That concat needs to have one little property. It needs to be associative. So think about addition. If you have A plus B plus C, it's the same thing as A plus B plus C. So if you create a type that has a concat method, then you have a semigroup, and they're awesome. Let's go one step further. You can also have monoids. What is a monoid? It's a semigroup. Why not? Which on top of that, so it's a semigroup, which on top of that has an empty method, which returns a neutral element for concat. Think 0 in the addition. So if you have whatever A plus 0, what you end up with is A. So 0 is a neutral element for the addition. So how would you use that? Well, let's define a sum type, which will be a monoid. And so we know that we need concat, self, other, and that will return self x. So the value my sum type has been lifted plus the other dot x. And that shouldn't be, oops, okay, that works in definition. So then if I do sum of 1, concat, sum of 2, it doesn't work because we need the empty method. So the neutral element, empty, so we can concat, so we define a sum type, we concat, and we can call it, we can keep on calling it, and if we call it with a neutral type, oops. No, I don't, sum 0, that's not what I want. Oops, my mistake. We need to stay in the type. And sum, I'm going to say empty, because that's what it is. Here we go. I didn't think I would get to there. So that's basically a very extensive vocabulary. But they're very simple definitions. I'm actually not quite sure how it really helps you deliver, artifacts that produce value for whoever is using them. But it's quite interesting, and it's not that complicated. You can hopefully have managed to demystify a little bit of what functional programmers are about. Thank you very much.
That was fascinating and enlightening. I honestly don't know what I'll do with that knowledge, but thank you so much.
I'm in the same place as you.
And a little gift from the organisers.
Thank you very much.
Thank you again.
Thank you.